Okay, now let us move on. We have now gone through all the symmetry elements in all the symmetry operations, as well as through all point groups. We can now start to apply our knowledge in order to determine point groups of molecules. So if you have experience with this and know about the properties of all the point groups, then you can actually just by looking at a molecule, in many cases say, well, this molecule belongs to this point group, and that molecule belongs to another point group. However, if you are not so experienced, there are guides that help you with that point group determination. And these guides ask you basically multiple consecutive questions that you can either answer with yes or no, and these yes or no answers pertaining the presence of certain symmetry elements lead you then to the correct point group. Okay, so on the following, I would like to present one of these guides, and then we will apply this guide to a particular example. All right, so in this guide here, our first question that we ask is, is there a proper rotational axis present in this molecule? So if the answer is no, then that means that this molecule must belong to a low symmetry point group. Okay, so now if the answer this question is no, and we know that, well, our molecule belongs to a low symmetry point, we'd like to know, well, which is this low symmetry point group? So to determine that, we next ask, is there an inversion center? So if the answer is yes, then the point group is Ci. If the answer is no, we ask the next question, which is there a mirror plane present? And if the answer is yes, then we know that it's the point group Cs. And if the answer is no, then we know that the point group is C1. Okay, so now we have basically probed for low symmetry point groups. So let us assume that now that the answer to our original question wasn't no, but yes, and we do have a proper rotational axis present in our molecule. The next question that we ask then is, do we have 6C5, 3C4, or 4C3 axes present? So with this question, we probe whether our molecule belongs to a high symmetry point group, because remember, it is a property of a high symmetry point group to have multiple principal axes. Okay, so the icosahedral point groups have 6C5, the octahedral point groups have 3C4s, and the tetrahedral point groups have 4C3s. So if the answer to this question is yes, then we know that we have a high symmetry point group molecule, and we now have to determine which high symmetry point group it is. In order to do this, we ask additional questions. So the first question we can ask is, well, are there 6 C5 axes? So if so, then that would be the property of an icosahedral point group. Okay. And would need to distinguish, well, what kind of icosahedral point group is it? We can then ask the next question, which is, do we have an inversion center present? So if we have an inversion center present, then we know it's point group IH. If the inversion center is absent, then that must be the rotational subgroup of the icosahedral point group IH, which is the point group I. Now, let us assume we do not have an icosahedral point group. If the answer of this question here is not yes, but no, then we can next ask, well, do we have 3 C4 axes? To this question, we ask, well, do we have an octahedral symmetry here? So if the answer is yes, then that must mean that we have octahedral symmetry. And next we can ask, do we have an inversion center? If the answer is yes, then we must have the point group OH. If the answer is no, then that means that we must have the rotational subgroup of the point group OH, which is O. Okay, last but not least, we can probe for tetrahedral symmetry. If the answer about the octahedral symmetry was no, it's not yes. So let us assume now the answer is no. Then we can ask, well, do we have 4 C3 axes? So this essentially probes for tetrahedral symmetry. So if the answer is yes, then we ask, well, do we have a sigma H mirror plane present? If that's the case, then the point group must be TH. If sorry, if the answer is no, then we ask, do we have dihedral mirror planes present? If that answer is yes, then we have the point group PD. If the answer is no, then we have the point group P. So now we have checked for all the high symmetry point groups. It could be that our molecule does not belong to a low symmetry point group, nor does it belong to a high symmetry point group. Could be an intermediate symmetry point group. So this would be the case if the answer to this question here about the multiple principal axes was not yes, but no. Okay. So next we would ask, do we have n C2 axes perpendicular to the principal axis Cn? So with this question, we probe for dihedral symmetry. Okay. So if the answer is yes, then we do have dihedral symmetry. Okay, and we have a dihedral group. If the answer is no, then it would have a rotational group. So let us first assume the answer to the question is yes. We would need to decide then what kind of dihedral group we actually have. So we ask follow-up questions in order to determine this. So the first question that we can ask is, do we have a horizontal mirror plane in addition to the NC2 axis that stand perpendicular to Cn? So if the answer is yes, then that must mean that the point group must be of the type DNH. Okay, and N would be an integer number. That would be obvious from the answer to this question over there. So if the answer is no, then we would ask, well, do we have dihedral mirror planes? If the answer to this question is yes, then we would know that we have point group of the type D and D. But if the answer is no, well, we would know, well, the point group type must be Dn. Okay, so let us assume now that the answer to this question here, whether there are n C2 axes perpendicular to Cn, hasn't been yes but no. That means that we would have to have a rotational group. We can now determine which rotational group we have. Okay, so we can ask next, what is there a sigma H mirror plane present? If yes, we would know that our point group is of the type CNH. If no, we ask whether we have a sigma V mirror plane present. If that's the case, then we know that the point group is of the type C and V. However, if the answer is no, then we can ask, well, do we have improper rotational axis, which has 2 times the order of the principal rotational axis? And if the answer is yes, then the point group type is S2n. But if no, our point group type is CN. So now our scheme is complete. And you see that with such a scheme, you can easily determine the point group of a molecule. So you do not have to memorize the scheme that I have presented. So if I ask you a question in the exam about point group determination, I would provide you the scheme, but I would expect that you can correctly apply. Let's apply the scheme now to a practical example. Okay, so here's a molecule. This is actually an organic molecule, not an inorganic molecule, but it doesn't matter. We can apply symmetry to all kinds of molecules. So this is a dibromophthalene, obviously. And the first question that we would ask is there a proper rotational axis present? So can any one of you tell me if we have a proper rotational axis?
I think there is.
Yes, that's correct. Can you say where it is and what order it has?
I think it comes out of the plane of the page towards us or the other side, and then it rotates it probably 180, so 2. I'm not sure though at all.
Yeah, that is actually correct. I have here another answer. This answer is no. The correct answer is actually yes. So we do have a principle. So we do have a proper rotational axis. And that proper rotational axis stands perpendicular to the plane of the molecule and goes through the center of this carbon-carbon bond here. Okay. So as we rotate around this axis, sorry, we rotate this bromine molecule here by 180 degrees into this position. And this bromine molecule here rotates by 180 degrees into this position over there. Okay. And the carbon atoms also swap up so that the 2 aromatic rings actually superimpose. Okay. So for instance, this carbon atom here would be moved into position of this carbon atom, and this carbon atom here would be moved into the position of this carbon atom over there. We could make similar exercises also with all the other carbon atoms and would see that they all superimpose. So we do have a proper rotational axis here, and in this case, the order of this axis would be 2. So what would be our next question? Our next question would be whether there are 6 C5s, 3 C4s, or 4 C3 axes. Okay. We have ruled out that we have a low symmetry point group now because we do have a proper rotational axis. The next question probes for high symmetry point group. So do we have 6 C5s, 3 C4s, or 4 C3s? Okay, one answer in the chat. The answer no is correct. Yeah, we do not have multiple principal axes of the order 5, 4, or 3. We only have our C2 axis. Okay, so certainly that's not a high symmetry point group. Okay, so therefore we have to go to the next question, which is, are there now n C2 axes perpendicular to the Cn axis that we already have found? Okay, so in this case, we would need to find 2 additional C2 axes in addition to the one that we have already found. So do we have 2 additional C2 axes? Here's an answer. Yes, the answer is correct. No is correct. Yes. We do not have those axes. Okay. So we can ask the next question, which now probes for which rotational subgroup we have. Okay, we've just ruled out that we have a dihedral group, so it must be a rotational group. So what was the next question according to our scheme? Do we have a horizontal mirror plane? The answer is first no, then it was yes. I agree with yes, so we do have a horizontal mirror plane. And this mirror plane is just the plane of the molecule. Okay, it's a horizontal mirror plane because it stands perpendicular to the principal axis. Now this is again a mirror plane in which the positions of the atoms do not move at all. No atom gets moved around, but like we discussed several times before, it doesn't mean that the mirror plane doesn't exist. So we do have a horizontal mirror plane, and that means that our point group is C2H. Yeah, we know that it's C2H because we determined in the very beginning that our principal axis is a C2 axis. Okay, so this is how you apply the scheme. So now, to finish up this chapter, we'd like to briefly talk about so-called Cairo point groups. So you've probably heard about chiral molecules in your organic classes. So a molecule is chiral when it belongs to a chiral point group. So when does it belong to a chiral point group? It belongs to a chiral point group when it only has a proper rotational axis, but no other symmetry elements except the identity. Okay. In a different way, we can also say a chiral molecule must not have an SN symmetry element, no improper rotational axis. Remember, this also includes the inversion center as well as the mirror planes, because an inversion center is the same as an S2 improper rotational reflection. And A mirror plane is nothing else but an S1 improper rotation. Okay. So the mirror image of a chiral molecule is called an enantiomer, and enantiomer cannot be superimposed. Okay? So you have here an example for this. So we have here bromochlorofluoromethane molecule. So this molecule does not have not have any symmetry elements besides the identity, not even a proper rotational axis. Therefore, it means that it's Cairo. In this case, it would belong to the point group C1. So the chirality implies that there's a mirror image to it, and that this mirror image cannot be superimposed with the original molecule. Okay, and in the form of this mirror image is shown here. And this mirror image would be called the enantiomer. So why is it a mirror image? It's because, well, this bromine here is mirrored from the right side to the left side. This fluorine here is no, wait a moment, no, I made a mistake. No. This is not the mirror image. This here is. So this bromine here is mirrored from the right side to the left side. This hydrogen here is mirrored from the left side to the right side. And this fluorine here is mirrored from the, well, front to the front. So it remains pointing to the front. So this molecule here is not the same as this molecule over there here. So this molecule over there here would actually be the same molecule as this one here. We could actually make it superimpose by just rotating. Okay, so if you rotated this via the around this carbon chlorine bond, okay, our fluorine here, which would originally point to the back, would now point to the front. Our hydrogen, which points to the front, would now point to the back, and our bromine, which was on the left, would now be on the right side. Okay, so this is a chiral molecule which has, well, pretty low symmetry, but not necessarily chiral molecules have low symmetry. So for instance, the rotational subgroups of the high symmetry point groups have high symmetry, but they're also chiral. So before we go to that, I also wanted to point out something else. We encountered this molecule here before, and we could ask, well, is this a chiral molecule? So maybe you can guess, is this chiral? So what you need to do is to see if you can see a symmetry element other than the identity and the proper rotational axis. If you can find a symmetry element other than the identity and the proper rotational axis, then it's not a chiral molecule. can you see a symmetry element other than the identity and the proper rotational axis? An inversion, yeah, correct. Remember, we use this molecule as an example for the point group Ci, and the point group Ci has an inversion center, which is C in the middle. And that means that this molecule is not a Chiral molecule. Okay. Note that this molecule has a carbon atom with 4 different substituents. Okay, so this carbon atom has a chlorine, a bromine, a hydrogen, and well, this group. Okay. So this shows that a carbon atom having 4 different substituents is not a rigid criterion for chirality. The absence of symmetry elements other than the identity and proper rotational axes. So please keep that in mind. All right, but now let's go to the Chiral molecules that have a lot of symmetry elements. Sure. So remember these molecules here, and here the snap dodecahedron had a lot of symmetry elements, but they are only proper rotational axes besides the identity. So there are no mirror planes, there are no inversions, there's no inversion center, and there are no improper rotational reflections. Okay? And that means that despite these molecules being pretty highly symmetric, they're still chiral. Okay. Then let us move on to the next subchapter. So we will stay with symmetry for a while, but we will now look at symmetry from a somewhat more mathematical standpoint. So you will learn that we can describe symmetry operations. So now something wrong with my presentation here. Don't know why this is. Cannot stop presentation anymore. So here we go. So we learned that we can describe symmetry operations mathematically as matrices. And to have a basic understanding of that is important because it helps you to understand character tables, which are very important to apply symmetry to chemistry, then in particular to construct molecular orbits. So therefore, in the following, I would like to show you how one can describe symmetry operations via matrices, which will then help you to understand what is called character tables. And then the next chapter, we will apply these character tables to molecular orbital theory. Okay. So now to approach this, we should first understand what a matrix is and how to multiply, how matrices can be multiplied with each other. So a matrix is nothing else but a mathematical construct of numbers that are arranged in rows and columns. And when you multiply two matrices with each other, then what you do is you multiply each row of the first matrix with each column of the second matrix. And that gives you the so-called multiplication matrix, which is just the product matrix of the two. Okay. So you can say that we have an initial matrix A with I rows and k columns, which we want to multiply sorry again, with other initial matrix B, which has k rows and j columns. So that gives a product matrix with I rows and j columns. So the number of rows of the product matrix is equal to the number of rows in the product in the initial matrix A, and the number of columns of the product matrix is equal to the number of columns in the initial matrix B. So it's important to realize that we can only multiply with two matrices with each other if the number of the columns of the first matrix is equal to the number of the rows of the second matrix, because only in this case the matrix multiplication rules can be applied, meaning that only then we can multiply each row of the first matrix with each column of the second matrix. Okay, so this may sound a little bit abstract. So let us apply this to one example here. So we have here two initial matrices, which are both so-called 2 times 2 matrices. So both have 2 rows and 2 columns. So first of all, we need to decide, can these matrices be multiplied with each other? The answer is yes. So according to these rules, this rule here, the number of the column of the first matrix is equal to the number of rows of the second matrix. So the number of columns of the first matrix is 2. The number of rows of the second matrix is also 2. Therefore, we can multiply. We must now multiply each row with each column. So what does that mean? Well, that means the following. We take the first number in the first row and multiply it with the first number of the first column of the second matrix. Then we take the second number of the first row and multiply it with the second number of the first column in the second matrix. Okay, and we add both of these numbers up, and that gives us the first number in the first row of the product matrix. Okay, so it's basically 1 times 7 plus 5 times 4. See this here? 1 times 7 plus 5 times 4. And then you just continue like that. So in the next step, you multiply the first row with the second column, and that gives 1 times 3 plus 5 times 8, and that gives you then the second term in the first row. And then you go from the first row here to the second row, because you have no further columns in the second matrix with which you can multiply. And then you multiply the first row with the first column. So that means you have to multiply 2 times 7, and you have to add to that 6 times 4, and that gives you the first character in the second row of the product matrix. Sorry about that. So last but not least, we have to multiply the second row with the second column. So it's 2 times 3 plus 6 times 8. You see this here. So this now determines the value of the product matrix, which are 27, 43, 38, and 54. Okay, now let's do one more example. And in this example, the two matrices do not have the same dimension. So the first one is a 1 times 3 matrix, and the second one is a 3 times 3 matrix. So here the number of rows is equal to 1, and the number of columns is equal to 3. Here the number of rows is equal to 3, and the number of columns is equal to 3. So this value has to be equal to that value. We see that this is the case, so we know that we can multiply our matrices. So let us just do this. We have to multiply the first row, in this case the only row, with the first column, and that gives just 1 times 1 plus 2 times 0 plus 3 times 0. Okay, see this here, 1 times 1 plus 2 times 0 plus 3 times 0. So then you multiply the first row with the second column, well, that gives 1 times 0 plus 2 times minus 1 plus 3 times 0. You see this here, 1 times 0 plus 2 times minus 1 plus 3 times 0. And last but not least, you multiply the the first row with the third column, which is, well, 1 times 0 plus 2 times 0 plus 3 times 1. 1 times 0 plus 2 times 0 plus 3 times 1. Okay, so you just sum this all up, and that gives overall that gives 1, minus 2, and 3. Okay, so the dimension of the product matrix is again 1 times 3 matrix. In this case. Okay, now let's do one more example. So now we multiply a 3 times 3 matrix with 3 times 1 matrix, 3 rows in 1 column. So first of all, can we do this? So the number of columns in the first matrix is 3. The number of rows in the second matrix is also 3. So we know that we can do the multiplication. So what will be the result? We again have to multiply each row with each column. So the first row would be this. The first column would be that. In this case, the first column would be our only column to consider. So we have 1 times 1 plus 0 times 2 plus 0 times 3. That would give our first character. And that's overall just 1. Okay, because 1 times 1 gives 1, and 0 times 2, well, that gives 0, and 0 times 3, well, that gives also 0. So we have no further columns to consider here. Therefore, we move to the next row here. And the next character, which would now be the character of our second row in the product matrix, would be 0 times 1 plus minus 1 times 2 plus 0 times 3. So that will give minus 2, because minus 1 times 2 gives minus 2, while 0 times 1 gives 0, and 0 times 3 also gives 0. So last but not least, we have to multiply the third row with our one and only column. Well, that gives 0 times 1 plus 0 times 2 plus 1 times 3. So that gives 3 overall. Okay? And we now see that our product matrix is a 3 times 1 matrix. Okay. Now, what does that all have to do with symmetry operations, and why can we describe symmetry operations as matrices? Essentially because symmetry operations transform coordinates, and coordinates can be described as matrices. So basically what a symmetry operation does is it transforms the matrix describing new coordinates from a matrix that describing old coordinates into new coordinates. Okay, so therefore, any matrix that, when multiplied with the matrix that represents all coordinates, gives us correctly the new coordinates of our object, would be a mathematical description of our symmetry operation. We would call it the transformation matrix associated with our symmetry operation. All right. Now, coordinates can be described by 3 vectors that point to the respective point in space. And we can apply this principle now by a concrete example. We choose our water molecule here. So now water molecule, as you know, can be described within a coordinate system, and we can, well, define this to be the x direction, this to be the y direction, and sorry, this the x direction, this the z direction, and our molecule lies within that xz plane, and the y direction perpendicular to the xz plane. All right. Now, any point in the molecule can be described by 3 vectors x, y, and z that represent the coordinates of each point in space that belongs to the molecule. So now we know that we have SC2 symmetry operations in the water molecule. And now we have to think about, well, how do the coordinates transform as we carry out the symmetry operation, C2? So the symmetry operation C2 is being carried out around the z-axis in the way we have defined our coordinate system. So what does that mean to the 3 vectors here that represent our coordinates? Okay. So as we rotate by 190 degrees here around the z-axis, well, our x coordinate will remain its value, but the algebraic sign of the coordinate will change. Or in the vectorial picture, our vector will have the same length, but it will point in the opposite direction. So now, what about the y-axis? So the y-axis, which here points to the back, will rotate by 180 degrees and now point to the front. That means that the y-coordinate will retain its value but change its algebraic sign. So the associated vector will keep its length but reverse its direction. So now what about the z-axis? So for the z-coordinate, nothing changes because we rotate around the z-axis. So now with this knowledge, we can say that, well, we transform our old coordinates into our new coordinates x prime, y prime, z prime, which are x minus x minus y and z. So you see that we have written the coordinates in a matrix form, namely in the form of a 3 times 1 matrix. So this would be the matrix for the old coordinates, and that would be the matrix for the new coordinates. Okay, so now the matrix form of our symmetry operation would need to give, well, the correct matrix for the new coordinates when multiplied with the old coordinates. So we can find this matrix by considering the multiplication rules of matrices. So in this case, the matrix that does the job is the form -1, 0, 0, 0, -1, 0, 0, 0, 1. We can verify that this is the correct matrix by applying the multiplication rules. So let's just do this. Let's multiply the first row here with the first and only column of the old coordinates. So this would give minus x plus 0 times y plus 0 times z. And that would just give minus x. So now we would need to multiply the second row with the first column. Well, what would that give? Well, that would give 0 times y plus minus 1 times y plus 1 times z. Okay, so 0 times x gives 0, 1 times 0 times z gives 0, but minus 1 times y gives minus y. This is exactly what we need. So last but not least, we need to multiply the third matrix, the third third row with the column here. So this will give 0 times x plus 0 times y plus 1 times z. Okay, well, that is just z. So now we have verified using the multiplication rules for matrices that this matrix here is the correct transformation matrix for the symmetry operation C2. In other words, you can say, well, this matrix here is a mathematical description of our symmetry operation. Okay, then I see our time is over. So let us stop at this point.